Okay, so this video is going to be about one of the most important concepts in this class, which is the idea of an LTI system. Okay, and you're going to be studying LTI systems throughout the rest of ECE 45 and also into ECE 101. Okay, so these are the systems that we study because they have properties that allow us to study them in a relatively easy way. Okay, they're pretty nice. All right, so in this video, I'm going to outline the definition of LTI and system. And then in the next video, I'll do some examples so you can get a hang for exactly what we're talking about. Okay, so what's our setup here? Well, we have some input, x of t. It's going to go into a box. And we're going to have some output, y of t. Okay. So right now I'm going to define system, which is defining this box. So what is that box? So far, we've seen that box as an RLC circuit, but at this point in the course, we're going to now start looking more generally at just general systems that may be RLC circuits, but they could be much more. Okay, they don't have to be RLC circuits. They could be anything, and I'll give some examples once I write the definition. So, okay, so a system is something, okay, and that is intentionally vague. Okay, it's something that takes time signals as inputs and produces time signals as outputs. Okay, so that's a system. So is an RLC circuit a system? Well, definitely. You put a time signal in and it goes through the system, and maybe you put it in as a voltage source, and then you read the voltage across some component in your circuit, and you get a time signal as an output. Okay, so that's RLC circuit is certainly a system. What else would be a system? Well, really any circuit, whether it's RLC or not, is definitely a system. If you put in some time signal and you get out some time signal by whatever means. What else could be a system? Well, this room I'm sitting in could even be thought of as a system, where the input is maybe the sound of my voice and the output is what you would hear if you were standing in this room. Okay, what you would hear standing in this room is not exactly just my voice. It's also my voice with the reflection off the walls. Maybe there's a little echo, reverberation, whatever it may be. That system of the room is coloring my voice in a certain way. And it's even more dramatic if you think of, a concert hall or something with an orchestra playing, right? You go to a concert hall to hear an orchestra, and you don't go to, some random room, because the room itself is designed to be a system that is conducive to making this orchestra sound better, right? It's specifically designed so that when you play music in it, the reverberations and the echoes or whatever, hopefully enhance the music in some way. Okay, so the input would be the orchestra's playing, and the output would be what you would actually hear in the room, which is certainly not just what you'd hear the orchestra playing, say, in a room with no echoes and no reverberation at all. Okay, so a system can be pretty general, and that's kind of a nice part of defining it this way, that we can take advantage of that generality so that things that we prove in this class will work in general for any system you have. And in this class, we're going to mainly look at systems that satisfy this LTI property. And it's actually two properties in one, the linear property and the time invariance property. So that's what we're going to define in a moment, but I just want to make one more point about another way we're making our definition here more general, and that's that the time signals can actually be complex valued. Okay, so we allow complex valued inputs and outputs. Okay, so complex numbers we're going to be working with throughout this whole class. And that's another way we're generalizing kind of what we looked at so far. RLC circuits, they're kind of things in the real world. We tend to put real valued inputs in, get real valued outputs out. Okay, but now for our general definition here, totally fine to have the inputs and outputs be complex valued. Okay. All right, so now on to the LTI part. And LTI, as I said, is two properties. One of them is the L, which stands for linearity, and the TI stands for time invariance. So LTI systems are systems that are both linear and time invariant. Okay, so there's three letters, but it's really only two properties. So let's look at the first one. That's linearity. Okay, this is a property of a system. Sometimes students get confused and think linearity might apply to a time signal. It doesn't. It applies to a system. So a system is linear. You can have a linear system if, okay, if whenever, I'm going to give you the condition, whenever I have two signals x1 and x2 and they produce outputs y1 and y2, that's all I'm writing here. The arrow, I use the arrow to say the thing on the left is the input, the thing on the right is the output. Okay, so whenever you have two inputs, x1 and x2, and they produce outputs y1 and y2, then the question is, what happens if I multiply x1 by some constant a and add it to x2 multiplied by some constant b? Okay. Now, what would be nice? What output would be nice from this input? Okay, what would you want to have happen? Well, I think, just kind of pattern recognition, you would love to have happen that what we get out is a times y1 and add to that b times y2. And it turns out that's exactly the condition we want for linearity. So a system is linear if whenever you give me two inputs x1 and x2 and any two constants a and b, and I combine all of those things in this way, I do a times x1 plus b times x2. Sometimes we call this a linear combination of x1 and x2, meaning I can take those two signals and multiply them by constants and add them. That would be a linear combination of those two signals. So this property is saying if I put any linear combination of x1 and x2 into my system, what I get out is the same linear combination of the outputs y1 and y2, meaning we have the same constants a and b, multiplying y1 and y2, and then we add them together. Okay, and this has to be true for any choices of constants a, b, and signals x1 and x2. So it doesn't just have to work for, some values of a and b and some signals x1 and x2. It has to be true for any of them. And by the way, a and b can be complex numbers too. So for the rest of the class, unless otherwise stated, pretty much everything we're looking at is going to be complex valued in general. So signals can be complex valued. These constants can be complex numbers. So complex numbers are going to be all over this class. Okay, so this is the property of linearity. And, it's kind of two properties in one. If I just let b be 0, I could get rid of these two terms and say, okay, if x1 produces y1, then I have to have essentially the scaling property that when I scale x1 by some constant, the output y1 is scaled by the same constant. And also as a special case, I could look at what if a and b are both 1? Then I can kind of forget about these a's and b's and say, all right, this is sort of an additivity property. Or if I take x1 and add it to x2, what should I get at the output? I should just get my outputs added together. Okay, so those are just two special cases, but in general, this entire line has to be true that any linear combination of x1 and x2 for any constants a and b has to produce that output. All right, so that's the definition of linearity. How about time invariance? Okay, well, a system, again, it's a property of systems. A system is time invariant if, okay, it's going to be a similar thing whenever I have some input x of t and it produces some output y of t, then let's just think for a moment about what do you think the output should be from this input? Now, what is happening in this input? Well, I have some signal x of t, and now I'm just picking some constant t naught, who knows, maybe it's 5, and I'm looking at the signal x of t minus 5, or t minus t naught. What is that signal? All I'm doing is delaying x by 5 time units, maybe 5 seconds, maybe 5 minutes, maybe 5 hours or days, it doesn't matter. I'm delaying x by some amount of time, or actually I could be advancing it. I could be starting it earlier if t naught was negative, like x of t plus 5, I'm kind of moving it farther into the past. Okay, but anyway, I'm shifting x by some amount in time. Okay, so let's just think of an example to try and guess what the output should be. You could probably guess already, but I want to really make sure we understand what's happening. Okay, so let's say x of t is like a certain song I want to play, and y of t is what you hear listening to that song through the speaker. Okay, so we're sitting here and I hit play, and then you hear the song coming out of the speaker. Okay, So the system is kind of like maybe my laptop and speaker. I hit play to start the song. I make that input go to the speaker, and then the output is what you hear. What would you expect to happen if we waited an hour and then I hit play again? Would you think it would be a completely different song you hear? Would you think it would suddenly be 10 times as loud? Would you think it suddenly plays backwards? No, it would be the exact same song you heard before, just started an hour later when I hit play an hour later, right? So it's the exact same thing you heard earlier, just delayed by the same amount. And that's exactly what the expression y of t minus t naught says. Okay, all this is saying is that if some input x produces some output y, then if I time shift my input, what I should get out is the same output I got before, just shifted by the same amount. I mean, it should make a lot of sense. And that's kind of true for both of these properties, that, you know, we chose to study these properties in part because it's not too restrictive. Like a lot of real world systems either are time invariant and linear, so LTI, or they're approximately LTI, and we can make that approximation and still get useful results. Okay, so hopefully these two properties seem pretty natural, and hopefully they make sense. And we're going to see a lot more examples in the next video, but I do have to add this one line. This has to be true, of course, for any choices of t naught and x of t. Okay, so again, it can't hold just for some time shifts or some signals. It has to be true for any of them. Okay. All right, so these are the two properties of linearity and time invariance, and we're going to be studying LTI systems pretty much for the rest of the class. Of course, you know, we might see some examples early on of systems that are not linear or not time invariant, just to kind of show you what these properties mean. But for the most part in this class, we're going to study LTI systems. And I just want to make a couple notes. Okay, so this one, I think you pretty much get the point, but I'll write it down anyway. We will write LTI to mean linear time invariant. Okay, so both. So LTI doesn't mean one or the other. It's both linear and time invariant. Okay, and the next thing is just that, as you might have guessed already, RLC circuits are LTI systems, right? Because all of the, you know, voltage and current relationships are either just multiplying by a constant in the case of resistors, or inductors and capacitors, we have different derivatives and integrals, right? But as we'll see actually in the example section, I'm going to look specifically at the differentiator and the integrator, two systems, where you put in input and either differentiate it or integrate it in a certain way. And we're going to show that those systems are LTI. Okay, so RLC circuits in general are LTI, and that kind of provides more of a bridge, right, between ECE 35 and 45, where we study LTI systems in general, because anything we prove in this class about LTI systems will then go back and apply in particular to RLC circuits, but we're going to prove it just using these two properties, linearity and time invariance. So it's much more general, and we can study a much wider variety of systems in this way by sort of abstracting away these properties that we care about, linearity and time invariance, and studying what happens to systems that satisfy those properties. Okay, so that's going to be sort of what we study for the rest of the class. And that is it for this video. In the next video, I will go over a whole bunch of examples so that hopefully we can get a feel, more of a feel for what these properties mean, and also get a feel for how to actually go about showing that certain systems are linear, time invariant, maybe not linear, maybe not time invariant, and so on, right? We want to try and learn how to actually show these properties are true or not. Okay, so I'll be in the next video, and I'll see you then.